Okay. Now instead of taking here, what we will do is we'll take a point at the bottom. Okay, and we say this whole angle which is there is alpha. If this height which is there is h, and if you know the length, you can you can always get this height. Understood? Clear? Is it clear? Shall I go to the next concept?
Yes, sir.
Now, from this, we have talked about something called as Pascal's law, right? So what your Pascal's law said is, if an external pressure is applied, external pressure is applied to an enclosed fluid, it is transmitted to every point in the fluid undiminished. This is called as Pascal's law. Okay. Understood? Then we have seen your Pascal's law as well, what Pascal law has said, right? After this, we have taken the condition of P minus P naught is equal to H, rho, and G. No, we have taken P is equal to H, rho, G, isn't it? From this, we have differentiated it. This became delta H into rho G. So delta P divided by delta H is equal to rho G, and this is called as
Pressure gradient.
Pressure gradient. And this is called as your pressure gradient. Now see, in this case also, if there is an atmospheric pressure here as PA, and the pressure here somewhere is P, so P is equal to PA plus H rho G, isn't it? Now take this PA that side, so P minus PA is equal to H rho G. Now P minus PA is delta H, and H is constant everywhere, so it comes here also, you will get the same thing. Understood?
Yes, sir.
So from this also we can prove your Pascal's law. So I'm going to take the above equation. This above equation I'm going to differentiate on both sides. So this will be delta PA plus delta of H rho G. And your delta of H rho G is constant, right? H rho G is constant for everything. No? The height is same, right?
Yes, sir.
Yes, sir.
So H rho G is constant. Delta of H rho G it's constant, so it just becomes 0. So your delta P becomes your delta PA. This also proves your Pascal's law. Understand?
Yes, sir.
Next, we have seen what is called as your atmospheric pressure. We have seen what is called as your atmospheric pressure. Okay, so the pressure, atmospheric pressure is defined as the pressure at any point. The pressure at any point, the pressure at any point is equal to the weight of a column of air, of U cross-sectional area, unit cross-sectional area I can write it as extending from the point to the top of atmosphere. So this is called as your atmospheric pressure. So atmospheric pressure at sea level, your PA value is 1.03 into 10 power 5 pascals. PA, where PA is called as your pascal. This is your unit of pressure as well. Other than Newton per meter square or Newton per mm square, you have learnt another unit called as Pascal. So 1.013 into 10 power 5 pascals. Okay. This is also termed as 1 atmosphere. So the unit of your pressure is atmosphere.
Yes, sir.
Now, how do we measure your atmosphere? Okay, to measure your atmosphere, we use an instrument called as barometer. We use an instrument called as barometer. Why? Because this bar, which is a BAR, this is a pressure. So pressure has another unit called as BAR, bar. Okay. So atmospheric pressure is measured by barometer, and gauge pressure. What is your gauge pressure formula?
Delta P by delta T.
PB minus not equal to rho GH.
Correct. P minus P naught is equal to rho GH. This is called as your gauge, right? So gauge pressure, we measure the gauge pressure by something called as manometer. Understood? Atmosphere, barometer, gauge pressure, manometer. Okay. Now, how do I get this barometer? Yesterday I told you a scientist Torricelli devised a method of measuring this atmospheric pressure. Okay. He has taken a U-shaped glass tube, and he has inverted that glass tube into a beaker of mercury. So slowly the mercury rises to the top, and to the top point he has calculated your pressure. So this is how your initial mercury based pressure measuring equipment was invented by scientist called as Torricelli. Okay, to commemorate his what should I say, invention in measuring the pressure is also measured in torr. Understood?
Yes, sir.
Okay. So the other unit for your press 1 torr, which is equal to 1 millimeter height of mercury, Hg. Hg is your mercury. In periodic table, if you see, you have something called as Hg. Okay. So 1 torr is equal to 1 mm of Hg. So torr is like short form of your Torricelli. He is a scientist, mercury-based barometer. Understood?
Yes.
Now I'm going to give you one important conversion table. Okay, you have to remember that conversion table. Okay, so 1 Pascal is equal to 1 Newton per meter square, which is equal to 10 dyne per centimeter square. Okay.
Yes, sir.
1 atmosphere is equal to 1.03 into 10 power 5 pascals, or this is 1.03 into 10 power 5 Newton per meter square. Okay. And 1 atmosphere is also equal to 76 centimeters of Hg, or this is equal to 760 Hg. 1 centimeter is 10 mm. Okay. Clear? Now, 1 torque is equal to 1 mm of Hg. Okay, so this is also equal to 1000 micro of Hg. 1 millimeter is equal to 1000 micro. Okay, but okay, take it. We generally don't use it, but then that's okay. Okay.
Yes, sir.
Now 1 mm of Hg is equal to 133.32 pascals, or 13.595 mm of water. Okay.
Yes, sir.
One second. I think there is just one more thing, because I have to use bar as well. I have to use bar. So, 1 bar, okay, BAR. 1 bar is equal to, we'll take approximately 1 into 10 power 5 Newton per meter square. Okay. Clear?
Yes, sir.
So torque to pascals did we get? Okay, let's take torque to pascals as well. Here, if you have space, put it as 133 pascals.
1 mm of Hg is equal to 133.32 pascals.
Then that's okay. So 1 bar is equal to 1 in 10 power 5 Newton per meter square, which is equal to 10 power 5 pascals. Okay. So once again, whenever you want to measure the pressure difference, you will use Whenever you want to measure pressure differences, you will use manometer. Whenever you want to measure atmospheric pressure, you will use
Barometer.
barometer. Remember that. Okay. So yesterday I told you to do this proof of Pascal's taking your hydraulic press. Did you do it?
Yes, sir.
Okay, so let me do that. It's a very simple one. See, I have taken a initially let me say piston here, and initially there is a piston here. So this is your A1 and this has your A2. Now let me say I'm applying a force of F1 here. So this piston will move here and this piston, let me say, comes here, right? So the pressure here at this point, if I draw a straight line, should be equal to the pressure here at this point. Yes or no? So when a force of F1 is acted on this, can I say a force of F2 acts on this?
Yes, sir.
Correct. Now, if a force of F1 is acting on area 1, the pressure which is acting is F1 by
A1.
A1, right? Now, I need the force F2 here, which is nothing but my pressure into area 2, right?
Yes, sir.
P2. But we know when it is in static condition, your pressures are equal.
Yes, sir.
So
Yes, sir.
I know my P1 is equal to P2. So F2 is equal to F1 divided by area 1 into area 2. So from that, F1 divided by F2 is equal to
A2 divided by A1.
F1 divided by F2
A2 divided by A1.
A1
Sorry.
divided by
A1 divided by A2.
divided by A2. So anyhow, so this can also be written as, it is called as your mechanical advantage. Where did you study mechanical advantage? Previously? Where did you study mechanical advantage previously? Torque. Yes. Principle of moments we have solved now. No? Yes or no? Anyhow. So this is your proof of your Pascal's law applied in your hydraulic machine. Clear? Shall I go to the next one? Now, okay, so I've completed Torricelli. So we'll talk more about your Torricelli. Okay. So before that, if I want to tell you your velocity of efflux, I have to come to your fluid dynamics. I have to talk about urine flow and steady flow. Reynolds number I have to tell you. So before that, okay, let me tell you the concept of buoyancy. Let me tell you the concept of buoyancy. Okay. Now, what do I mean by a buoyant force or buoyancy? See, whenever you place a body inside a liquid, so for example, I'm going to take a beaker, and inside the beaker, I'm going to place an object. inside the beaker, I'm not placing object. So this is everything is in water, let me say. Everything is in water. So the beaker basically is immersed in water. See, from here to here, this height I will take it as D1, and from here to here, this height I will take it as D2. From here to here, this height I will take it as H. Okay. So density of your liquid, density of liquid, I'm going to take it as, and the density of the body, I'm going to take it as some sigma. Okay.
Yes, sir.
Now let us see what do you mean by Bion's force. See, whenever the body is placed inside a liquid, this liquid tries to exert force on this body, right?
Yes, sir.
Yes, sir.
So top point, let me say the force is F1, and your bottom point, let me say the force is F2. So if your resultant force on this body is greater at bottom, then the bottom part will come front like this and the body will float. If your F1 is greater than your F2, then the body tries to go inside. Apart from your only affected by your liquid, the density of the body also plays an important role. Okay. So first of all, we'll just see what your Bion's force is. So we define your Bion force as the net resulting force which the body experiences vertically upward direction, and this is exerted by your, this is called as your Bion force, or also called as your buoyancy. Okay. Now tell me, this is your point 1, this is your point 2. Now tell me, what is your pressure 1?
Atmospheric pressure plus.
What is your pressure at 1?
Density of the water plus
Atmospheric pressure plus rho G D1, isn't it?
yes, sir.
What is your pressure at 2?
Atmospheric pressure plus rho G.
Rho GD2.
D2. Correct? Now I'm going to assume the area of to be A. If this is your pressure, what is your force exerted there? P1 into area.
Yes, sir.
So this will be PA plus rho GD1 into your area. From here, F2 is equal to P2 into A, which is equal to PA plus rho GD2 into area, right? So what is your net force acting on this body?
F1.
F2 minus F1.
Yes, sir.
Yes, sir.
So
P taken common.
PA into A plus rho GD2 into A minus A into PA minus rho GD1. This and this gets cancelled. So A rho G I'm taking common, it is D2 minus D1.
Which is H.
But D2 minus D1 is height of your body, isn't it?
Yes, sir.
So this is equal to rho G Area into height will give you what?
Volume.
Volume. Rho V. So this is called as your buoyant force.
So it's volume of the liquid.
Yes. No, this is volume of your body.
Oh, okay, okay.
Understood?
Yes, sir.
Clear?
Yes, sir.
So the scientist who has given you the concept of buoyant force or buoyancy is called as Archimedes. You have studied your Archimedes principle. In your 10th class, you must have studied your Archimedes principle, isn't it? Yes or no? So, have you taken this derivation down?
1 minute, sir.
Yeah, yeah. So, FB is equal to rho GV. See the beauty of your physics. We are telling F is equal to mg, no?
Yes, sir.
M is
Density into volume.
Density into volume.
you got rho Vg, rho Vg.
Yes, sir.
Now again see, F is equal to mg, which is nothing but rho V into G. So rho area into H into G is your F. Take your F here. Pressure is equal to, take your A here. F by A is
Pressure.
Pressure.
yes.
Sure.
Yes, sir.
Even if you suddenly forget your formula, you can always derive it. Understood?
Yes.
Have you taken it down?
Yes, sir.
Below that, the buoyant force on a body, the buoyant force on a body, the buoyant force on a body, buoyant force on a body immersed in a fluid, immersed in a fluid, immersed in a fluid, immersed in a fluid is equal to is equal to is equal to the weight of the fluid, the weight of the fluid displaced by that body, displaced by that body, displaced by that body. Can anybody just repeat it?
The buoyant force on a body immersed in a fluid is equal to the weight of the fluid displaced by the body.
By that body. Okay. So from this we say your buoyant force is basically the resistance force. Okay. See here at this you can write rho is density of liquid. Okay, and V is volume of body. Understand? Please take it down or else you may get confused. Done?
Yes, sir.
Yes, sir.
Now, case 1. If your force due to gravity, which is also called as weight, is greater than your Bion's force.
The body gets
Body will sink.
Yes, body will sink. Okay, understood?
Yes,
This
sir.
is also called as negative buoyancy. Case 2. If Fg, that is force due to gravity or weight, is less than your Fb, then
The body will float.
body will float.
body will float. This is called as your positive buoyancy. Understood? Case 3. If Fg or weight is equal to Fb, then
Body will be at equilibrium.
body will just sink. Okay? This is called as your nodal buoyancy. Understood? So, see, if you take a body, if this is your liquid, negative buoyancy, that means your Fg is greater than Fb, so your body will be like this. Okay? And if you're talking about your case 2, that is your positive buoyancy, something like this. And if you're talking about your neutral buoyancy, the body will be like this. Understood? Clear?
Yes, sir.
Now, take your densities on both sides. So density of your body, here it will be greater than your density of, we'll say L, liquid. Yes? Here, your density of your body is less than density of your liquid. Here, density of your body is equal to density of your liquid. Understand? Oh, have you taken it down?
1 minute, sir.
Yeah.
Done, sir.
Over?
Yes, sir.
Now, take down again. If two liquids, if two liquids of equal masses, if two liquids of equal masses but different densities are mixed in a container. If two liquids of equal masses but different densities are mixed in a container, then find the density of the mixture. Find the density of the mixture.
So can you please repeat the
If two liquids of equal masses but different densities are mixed in a container, then density of the mixture is M1 is equal to M2 is equal to M, right? Density of liquid 1 is rho 1 and density of liquid 2 is rho 2. Find the density of the mixture. See, tell me this. I have taken 5 ml of liquid 1. I have taken, this is liquid 2, 10 ml of liquid 2. I have taken a container whose capacity is 30 ml. When I pour these two liquids in, what happens?
half the capacity is filled?
What do you mean by that? What is the volume in this now?
15 ml, which is V1 plus V2.
So V of your mixture is nothing but V1 plus V2, right? Yes or no?
Yes, sir.
Correct. So it has total mass divided by total density is equal to M1 divided by rho 1 plus M2 divided by rho 2.
Yes, sir.
What is your total mass?
M1 plus M2.
Divided by rho mixture to M1 divided by rho 1 plus M2 divided by rho 2. But M1 and M2 is equal to M, same mass he said.
Yes, sir. So it's
It will be
2.
2M divided by rho mixture is equal to M divided by rho 1 plus M divided by rho 2. Rho mixture will be equal to 2 times of rho 1, rho 2 divided by Clear?
Yes, sir.
Over. Shall I go to the next question?
Yes, sir.
In the above question 2, in the above question, if the masses are, if the masses are different, but volumes are, if masses are different but volumes are same, then the density of the mixture is, then the density of the mixture is. So now your volumes are same but masses are different. Okay. Clear?
Yes, sir.
Now you tell me what is your resultant density.
Sir, rho of mix is rho by 2.
Yes. If volumes are constant, rho mixture is equal to rho 1 plus rho 2 divided by 2. If masses are constant, then rho mixture is equal to 2 rho 1 rho 2 divided by rho 1 plus rho 2. Clear?
Yes, sir.
Shall I go to the next one?
Yes, sir.
See, I am telling you once again, whenever you have a doubt, picture your problem like this, okay? That will be very easy. As such, fluid statics is that's all. We have to go to fluid dynamics. Okay. Let me just see some problems for you on your fluid statics. There are not much problems on fluid statics. Take down this problem. The two famous, in brackets, these are called as your thigh bones. The two famous, each of cross-sectional area, the two famous, each of cross-sectional area 10 centimeter square, 10 centimeter square, support the upper part of the human body, support the upper part of the human body, support the upper part of a human body of mass 40 kg, of mass 40 kg, of mass 40 kg, full stop. Estimate the average pressure sustained by the, estimate the average pressure sustained by the femurs.
So once please repeat the question. The last part, sir. Estimate the average.
Pressure sustained by the femurs.
Thank you, sir.
What is your area given?
10 centimeters square.
10 centimeters square.
So,
Convert into meters square.
mass is given as,
40 kg.
40 kgs.
so from this your weight is,
400 newtons.
400.
or this is also your force.
Force.
Now see, area of one femur bone is 10 centimeters. Therefore, total area is,
20
20
centimeters.
centimeters square.
which is equal to 20 into 10 power minus
Minus
4
4 meters square.
meter square. So pressure is equal to force by area. So 400 newtons divided by
20 into 10
20
power
power
minus
minus
4.
4.
meters.
2 into 10 power minus 5. 2 into 10 power 5.
Power 4 newton per meter square. Okay.
There's 2 atmosphere.
No. See, you don't, see, atmospheres you will only use when it is inside your fluid. Okay.
Okay, yes, sir.
Anything which has a solid one, pressure, whenever pressure is coming in the context of your solids, Newton per meter square. Whenever your pressure is coming in the context of your air, generally we'll use your mm of Hg or the atmospheres and everything. Okay.
Yes.
Whenever your pressure is coming in the context of your fluids and everything, we'll use pascals or something.
Yes, sir.
So water, whenever fluid it's coming, we'll use atmospheres or pascals or anything.
Yes, sir.
So take down your next question. What is the pressure? What is the pressure on a swimmer? On a swimmer, what is the pressure on a swimmer 10 meters 10 meters below the surface of lake? What is the pressure on a swimmer 10 meters below the surface of a lake? Take G is equal to 10 meters per second square. Take G is equal to 10 meters per second square. Density is equal to 1000 kg per cube. Density is equal to 1000 kg per meter cube. So find the pressure.
So is it 2 atmosphere?
It is 2 atmosphere. Over. Shall I go to the next question? So you have to use your formula. P is equal to P naught plus
Plus rho GH.
rho GH. Next, the force acting on the window of the force acting on the window of the force acting on the window of a submarine at a depth of 1000 meters at a 1000 meters at a depth of 1000 meters in an ocean is the force acting on the window of a submarine at depth of 1000 meters in an ocean is density is 1.03 into 10 power 3 kg per meter cube. G is equal to 10 meters per second square and area is 20 centimeters divided by 20 centimeters. Usual atmospheric pressure taken as 1 into 10 power 5 pascals.
Is it 416 into 10 power 3 Newton?
4
into 10 power 3.
Yes. See, what is your area? 20 into 20, which is 4 into 10 power 2 centimeters square, which is 10 power 2 in minus 4. So how much is it?
4 into 10 power minus 2.
Meter square is your area.
Yes, sir.
Now height is given as
1000 meter.
1000 meters. So first calculate your pressure at that point. PA plus rho G H is 10 power 5 pascals plus density is 1000 G per meter cube
Yes,
is 10 meter per second square into 1000 meters, right?
density is 1030.
Huh?
The density is 1030.
Okay, I've given you a different value. How much is it?
1.03 into 10 power
10 power 3. Yeah? Okay. So your pressure at that will be
104 into 10 power 5 pascals
104
into 10 power 5.
power 5 Pascal. Pascal is Newton per meter square. So we'll place it like this. Okay. He's asking force, and force we need it in newtons.
The force is
So force is equal to pressure in area. So 104 into 10 power 5 Pascal is Newton per
meter square.
square is 4 into 10 power minus meter square. So let's cancel. For 4 16s, 416 into
10 power 3.
3 newtons. So 416 kilonewtons is force acting on a submarine
Depth of 1000.
only on a window of 20 centimeter by 20. Your scale and draw your 20 centimeter by 20 centimeter. How much small window is it? On that window, how much force is acting? 416 kilonewtons. Understood? Understood? If you want, divide this with your G. So it will be 416 into 100 kgs. So 41600. 41,600 kg weight if you put on a 20 by 20 centimeter. Imagine how much it is. Understood?
Yes, sir.
So 41.6 tons of weight is acting on your 20 centimeter by 20 centimeter weight only at 1 kilometer depth. Just go to 2, 3, 4, 5, 6, 7 like that. You see how much your force acting on it? Understood?
Yes, sir.
Shall we go to the next one?
Yes, sir.
Okay. The fundamental problems. Let's put your heading as variation of pressure with altitude. Now, see, whenever we are going to a height greater than your sea level, we will see that it's becoming more and more thin, right? So that's why the people who are doing mountain climbing, for example, let me say they are trying to climb Mount Everest or Fiji mountain, okay, they carry oxygen cylinders with them, okay, they carry oxygen cylinders with them. You know this, right?
Yes, sir.
Yes, sir.
So why do they carry oxygen cylinder? Because when you are climbing to the top of a mountain, the air becomes thin. That's because your pressure is changing. Okay, so when the pressure is changing, your air becomes thin, so it will be difficult for us human beings to sustain there for a longer time. Now, how does your pressure vary with your altitude? So that's what we are going to see. Since when we are talking about your pressure variation with respect to altitude, can I say we are talking mainly of gas?
Yes, sir.
Air, of course, but then all the laws of gas can be applied to your air, isn't it?
Yes, sir.
Now tell me, what is the relation between your pressure and density and temperature?
P1 by rho 1 to P2 by rho 2 T2.
Yes. Okay. So, do you remember this P by rho is equal to, no, P by rho, right? Is equal to Kp by M.
Yes, sir. Boltzmann constant temperature.
So, for example, you forgot this. Okay, but variation of pressure with altitude. And we know we can apply your gas law for this also, right?
So P1 V1 by T.
I can apply, right?
Yes,
So
sir.
how easily I'll get it for you. Density is equal to
Mass by volume.
mass by volume. Now, mass is nothing but your number of moles, Avogadro number in your mass of one molecule.
Yes, sir.
I know PV is equal to nRT, isn't it?
So V is NRT by T.
NRT divided by T. N gets cancelled. R by NA is Boltzmann constant.
Yes, sir.
P goes up. P into mass of one molecule divided by Boltzmann constant into absolute temperature is density.
Yes, sir.
That's what it is. How to become very easy with your subject. Okay. See, I'm deriving the whole gas law from the basic formula of mass by volume. Is it clear?
Yes, sir.
Yes, sir.
Okay. So from this, I don't think you need a derivation for this because now we see rho is equal to Pm by kBT. This is your this one. Okay. From here, we'll try to prove your get a general equation for your variation of pressure with respect to altitude. Okay. Now I know my delta P is nothing but minus rho G A into delta H divided by area.
Yes, sir.
Yes.
Yes, sir.
So area and area gets cancelled. This will be minus rho G delta H.
Yes, sir.
So from this delta P divided by delta H is equal to, okay. Now I'll just rewrite this terms. Let's see, it will be the minus G capital P divided by KBT.
Yes, sir.
I'm just rewriting it. See, density is Pm divided by KBT normal. So instead of density, I'm replacing it with this, right? So I got mg into P by kBT. Pm by kBT substituting, I get mp by kBT, right? Yeah. Now this I will integrate it, okay, on both sides. So what I will get is pressure at a height is equal to initial pressure P naught into e power minus mg divided by kb into t. Understand? Clear?
Yes, sir.
So we integrated this, sir.
Huh?
From coming to this step to that step, we integrated. Yes, sir.
All right. So that's it. That is difficult. Just gave the direct one. Okay. So from this formula, you can always find your pressure of a pressure at an altitude h. Okay.
Yes, sir.
Clear?
Yes, sir.
So this is not in your syllabus, but this I told you, keeping in view your mains. Okay.
Yes, sir.
Because in mains it is important. Okay. So, okay. Yeah. Nikita,
Yes, sir.
just recap what we have done today.
Sir, from the starting of the class.
Yeah, from today, only for today.
Okay, sir. First, we started with the pressure, which is the normal formula of pressure, which is F by A. We studied about the SI units of pressure. We saw that the pressure depends upon the atmospheric pressure, the density, depth, and even G.
Hmm.
Then we studied that it is independent of the amount of the fluid, and it is even independent of the shape of the container which it is kept in.
Hmm.
Then we learnt about the gauge pressure, which is nothing but P minus P naught, which is equal to rho G head.
Gauge pressure. Hmm.
Okay, so gauge pressure. And then we learnt about the static liquid.
Hmm.
There we learned that if it is in the same line, then the pressure is going to be constant at all the points.
Hmm.
Then we learned about the Pascal's law. Pascal's law, under that P is equal to rho G H. After that, we got delta P by delta H, which is equal to rho G, which is also known as the pressure gradient. After that, so we when next we learned about the atmospheric pressure.
Hmm.
So at atmospheric pressure, we came to the definition of it, and then we came like what is at the sea level, what is the atmospheric pressure, which is nothing but 1.03 into 10 power 5 Pascal. Then which is further equal to 1 atom. I mean 1 atmosphere. Then further we learnt about the barometer, barometer is used to measure the atmospheric pressure. Then gauge pressure is measured by this manometer. Next, then we learnt about the Torricelli scientist, who was the scientist who had first invented the mercury-based thermometer. Then from that, from his
Mercury
from the
based.
manometer, sorry.
Yeah,
Then
not
we learnt, yeah, sorry, sir. And then we learnt about this from that scientist. We have the word known as torr, which is also one of the we use it for pressure. It is one of the unit. So 1 torr is equal to 1 mm of Hg. Then we learnt about this the different scales, like in Pascal, atmosphere, torr. What are the values separately we learned? Like if they have given us one, how to convert it into the other form. Then we have learnt about